Welcome to This Explainer. I'm your host, Dr. Chem, and today we're embarking on what is honestly a truly breathtaking journey. We are diving deep into humanity's quest to observe the invisible, mind-bendingly fast quantum dance of molecules. We're talking about ultrafast laser spectroscopy. Imagine a cinematic documentary where we zoom all the way down into the atomic world, where molecules are vibrating, electrons are shifting, and chemical bonds are transforming in ways you can hardly imagine. In this explainer, we're going to see exactly how scientists are using some incredibly cutting-edge, neon-lit optical instruments to literally freeze time itself. So let's start with a dramatic journey through time. You and I, we all know what a second feels like, right? But let's accelerate down to a millisecond, a microsecond, a nanosecond, a picosecond, and finally a femtosecond, 1/millionth of 1/billionth of a second. To put that into perspective for you, a single femtosecond is to 1 second what 1 second is to about 31.7 million years. At this unimaginably short time scale, chemical reactions don't just gently happen, they practically explode into existence. To capture these super fleeting events, like the vibration of a single chemical bond or the transfer of just one electron, we obviously can't use standard equipment. We need the ultimate slow-motion camera. And that ultimate camera? That is ultrafast laser spectroscopy. It's an absolutely revolutionary technique that uses ultra-short laser pulses to capture molecular dynamics right there on the femtosecond scale. Essentially, think of this as laser physics, but applied completely from the perspective of a chemist. The problem we have is simple. Chemical reactions happen way too fast to see. So the solution? We use these incredibly brief pulses of light to illuminate and record these invisible, high-speed quantum events exactly as they unfold in real time. Okay, let's dive into Section 1, the pump-probe principle, or as I like to call it, the chase sequence. Now, you might be wondering, how do we actually measure something that happens in a single femtosecond? Well, we use this microscopic chase sequence. Step 1, we fire a high-intensity pump laser pulse. You can think of this as the instigator. It hits the sample, excites the molecules, and ignites the reaction. Step 2, an optical delay stage introduces a very precise time delay. Then, step 3, we send in a weaker probe pulse. This probe acts like a tiny detective, arriving femtoseconds later to photograph the aftermath, basically by measuring the change in the sample's absorbance. By just slightly tweaking that delay between the pump and the probe, we can actually stitch together a flawless frame-by-frame movie of the entire reaction. Just think about the sheer complexity of the lab setup required to make this whole thing happen. Picture a futuristic room, illuminated by these glowing blue and purple laser beams routing all over the place. That's the optical pathway of a femtosecond transient absorption spectrometer. The pump path and the probe path have to be incredibly carefully routed through a maze of beam splitters and mirrors until they overlap, spatially and temporally, exactly at the sample. Time zero is that exact, highly calibrated fraction of a femtosecond when both pulses hit the target simultaneously. Moving right along to Section 2, building the ultrafast lab and the precision optics involved. To control light at this microscopic scale, you need a seriously advanced laboratory. The conceptual architecture of a femtosecond optical parametric amplifier, or OPA, is a marvel. The optical pathways are wild. We usually start with a fixed-frequency laser source like a state-of-the-art titanium sapphire or ytterbium system. But here's the catch. Chemists need to tune their lasers to specific colors or frequencies so they perfectly match the exact absorption band of the molecule they're studying. That is exactly where this beautiful labyrinth of delay lines, seed generation, and amplification stages comes into play. And this brilliantly illustrates what happens at the quantum level. Think of the OPA as a photon cutter. You send in a high-energy pump photon, and the nonlinear crystal inside the OPA quite literally splits it into two lower-energy photons, which we call the signal and the Euler. By adjusting the angles of that crystal, we can tune the exact frequency of the outgoing light. It gives us a laser beam in pretty much any color we need to probe our sample. And this is exactly why OPAs are completely ubiquitous in ultrafast laser labs today. They offer continuously variable frequencies, meaning we can tune them seamlessly from the mid-infrared all the way up to the visible spectrum. They act as broadband amplifiers, transferring energy from a narrowband pump to create the exact incredibly short pulse needed to hit molecular resonance. Honestly, without this technology, tuning our ultrafast camera flash to the right color would be completely impossible. Section 3, decoding the data. Let's map this quantum dance. So what actually happens when that light hits a molecule? Well, we get this really elegant map of molecular energy known as a Jablonski diagram. When the pump laser hits a molecule, like the subnanoclusters often studied in these labs, it kicks an electron right up from its relaxed ground state, which we call S0, up to an excited state, S1. From there, the molecule has to relax. It might emit light through fluorescence, maybe lose energy as heat through internal conversion, or even undergo intersystem crossing to a triplet state, T1. Our delayed probe pulse captures all these transitions as they happen, allowing us to build this highly dynamic model of exactly where the energy goes. All right, Section 4, mapping molecules in 2D, using 2D electronic spectroscopy. Now, scientists always want more detail, right? If standard transient absorption is basically a 1D movie, two-dimensional electronic spectroscopy, or 2DS, is the next huge evolution in our toolset. And the magic number here is 3. While your standard pump probe uses 2 pulses, 2DS fires a sequence of 3 incredibly precise laser pulses at the sample. The first pulse pumps the system into a coherent state, the second pushes it into a non-oscillating state, and the third probes it, generating a measurable echo. This lets us map both the excitation frequencies and the detection frequencies onto a highly complex 2D grid. When you look at a 2DS map, you get 2 main types of data. The diagonal peaks show us where the signal oscillates at the exact same frequency it was excited at, which is basically what we already knew. But the cross peaks, those are an absolute game changer. They're the holy grail. Cross peaks appear off the diagonal, and they prove that the system is actually emitting at a completely different frequency than it was pumped with. This directly reveals those hidden energy transfers, charge separations, and super complex quantum couplings between different molecules. Section 5, from photosynthesis to quantum. The real-world impacts. So the crucial point is, why does mapping these femtosecond energy transfers matter to us outside of a dark laser lab? Well, the applications are truly staggering. Biologists are using these techniques to track how plants achieve near-perfect charge separation during photosynthesis, literally paving the way for next-generation solar energy. Medical researchers are tracking the excited state dynamics of DNA to understand exactly how UV light causes skin cancer. Chemists use it to study sub-nanoclusters for photodynamic cancer therapies. And material scientists, they're using it to observe electron-phonon coupling to build insanely fast quantum semiconductors. There's this fantastic quote from the Journal of Physical Chemistry Letters that sums it up perfectly. The frontier in quantum materials lies in precision measurement itself, where rigor becomes the engine of discovery. We aren't just passively observing nature anymore. Our ability to measure it with sharper and sharper resolution is actively uncovering completely new physics. Section 6, the future of ultrafast. Let's look beyond the femtosecond. So where do we go from here? We've basically conquered the femtosecond, and the horizon is incredibly bright. We're actually moving beyond the femtosecond down to the attosecond, which is 1,000 times faster, using attosecond chronoscopy to track the movement of individual electrons in real time. We're developing tabletop X-ray pulses to look at atomic structures right as they break apart. And of course, we are integrating AI-assisted platforms to instantly decode the massive multidimensional datasets generated by all these techniques. Which leaves us with a pretty mind-blowing thought to end this explainer on. If we can already freeze a glowing molecule in a single femtosecond, deciphering the very mechanisms of life and energy, what profound secrets of the universe are we going to uncover when we zoom in even further? The ultimate slow-motion camera is only getting faster, and the quantum dance is finally revealing its steps. Thanks so much for joining me on this deep dive.